Simple harmonic motion part 2. So let's just quickly review. Simple harmonic motion, we said, is any motion whose characteristic equation conforms to the following pattern. The second derivative of some position function is equal to negative some constant, which we're going to call omega squared, times that same position function. Okay? And so in our specific example here, we had d squared x, dt squared was equal to negative omega squared x, where for the simple harmonic oscillator, omega was equal to radical k over m. This is very specific to the context. Now, that generated the following equations of motion, that a was equal to a cosine of omega t plus phi, where phi was something, I don't actually think I wrote this down, the phase angle, and that phi had everything to do with, or was determined by the starting position, right? Okay. That v had to therefore then be negative a omega sine of omega t plus phi, and that a had to equal negative a omega squared cosine of omega t plus phi. Now, if I had written this so that the object started at the equilibrium position, had a speed at that position, I wouldn't have to do this way. I could say a was equal to negative a sine omega t plus phi, and then that would just like change the v and the a in terms of the negative sign and whether this is a sine or cosine. Or just the easy way to do it is just with a phi. So two ways that you can account for the initial position. You can have a phi factor here, or if you don't want to have that, you can change sines to cosines or cosines to negative signs. If you're starting at the extreme positions or at the center, if you're starting at some sort of intermediary position though, you're going to have to do it with a phi. Anyway, that's sort of like what we got. So I want to do two things here. I want to first address this omega because that's something that I think people are probably looking at this going, I don't understand why we have a term for rotational motion in something that is vibrating back and forth linearly. Okay, I'm going to resolve that question. And then what we're going to do is how can I make the math work and prove that I get the same math using a rigorous mathematical process, which we'll then abstract. So let's deal with that first. Because usually when we encounter omega, what we're really doing is we are looking at something going around in a circle, right? So let me just draw the unit circle, okay? Because usually, you know, this term here would be like a theta, right? And so I might have my position here r to that point, right? And this is x, and then this is some other axis here. And so, you know, if there's an omega, then omega would be equal to d theta dt, right? So let's say omega is a constant, so that this thing is changing angles at a constant rate. That means that I could say that delta theta would be equal to omega delta t. That's assuming omega is a constant, right? So that's fine. Or there, I could also say then, therefore, that any theta is equal to omega t plus some sort of initial theta, yeah? Well, that looks familiar. If I call the initial theta a phase angle, that is pretty much identical to the argument of that term there. Okay, great. But still, like, great, so this object going around in a circle, right? This object going around in a circle, but that's not what's happening. The simple harmonic motion is going back and forth. And remember what we said, is it speeds up, slows down, speeds up, slows down, speeds up, slows down, right? So that's the motion there. But this thing is a motion around at a constant speed, right? So it goes around the tangent at a constant speed, right? So it goes around the tangent at a constant speed. Now, I just flipped the circle. So rather than doing this, I flip the circle to vertical. So if you want to think about it, folks, really all you're able to now see is that, I mean, I guess you could see some of the depth changes in terms of the field of vision, but really what you're seeing is a back and forth motion. right? Because simple harmonic motion is actually a circular motion. What? Ready? Let's say that this second axis is the imaginary axis, and that rather than a y component, we have an imaginary component. And rather than calling this r, we call this a. Notice here that what is the x component of this motion? Well, the x component here would be a cosine theta, right? And if our theta is equal to omega t plus some sort of initial angle, so phi, we get the same result. Because that's really what's true about simple harmonic motion, is that if we had something moving around in a circle, simple harmonic motion is the projection of a circular motion into one dimension. And all we're seeing is that one dimension, and the other dimension is imaginary. What? That's crazy. Imaginary? Where on earth would we get imaginary numbers from? We're talking about a real thing, but still it works. So an object moving at a constant speed around this circle, and if we were only constrained to look at the projection into the x-plane, we would see that constant circular motion as something that is moving back and forth at consistently changing speeds. So that's why we have the omega term in there. It is related to circular motion. There's a reason why angular frequency and angular velocity use the same terminology. And that's so crazy. Isn't that so crazy? That's awesome. Anyway, let's get some rigorous work down here. We have already said in terms of sum of forces is equal to ma, right? And this specifically, let's just call that a sub x because I'm doing sum of forces in x. And we said that in this fs was equal to max, and therefore negative kx is equal to max. All right, so a way of proving whether or not something is in simple harmonic motion often comes from writing a sum of force equation. Because now take a look at this. I've got negative k over m x is equal to, and this is just d squared x dt squared. Okay? That's all that is. And so this fits the definition of what we said is simple harmonic motion. We've got the second derivative of a position function is equal to negative that same position function times a constant. Right? So looking at this, I know that this is that constant. That must mean that, therefore, for simple harmonic, the simple harmonic oscillator, omega squared is k over m, and omega is equal to radical k over m from our previous work. That gels. Okay? But let's look at this a little bit more rigorously, and how would we solve that if we hadn't done all that other work? Right? How would we solve this for real? Well, if I look at this, I'm going to put this in a normalizable format. Okay, and I'm going to write it as a second order homogeneous differential equation. So what does that mean, second order homogeneous differential equation? Let me write that phrase down. We talked about this before. Second order homogeneous differential equation. So, pretty simple here. Differential equation, there's derivatives in it. Second order, the highest derivative is at order 2. Homogeneous, when all the terms of x are on the same side, that the other side is 0. So that's what makes this a homogeneous differential equation. And so we started saying, well, what had to be true about this function, the solution to this function? Well, what has to be true about this solution to this function is I need a function whose second derivative is the negative of itself, right? So what we're going to do is we're going to actually abstract this down, because what I want to show you is what the generic form of a second order homogeneous differential equation is. And we'll do this as an equation of x. And so the standard form looks something like this. D squared x dt squared plus, and then I'm just going to put p here, dx dt plus qx. This is what's called the standard form of a second order homogeneous differential equation. Why P and Q? Don't worry, that's just what gets done. Right? Now, in more complicated versions of this, P and Q don't have to be constants. They themselves could be functions, which changes the way in which we approach this problem, but the general idea is still the same. And so if we look at this, I need all of this to equal 0. Well, the problem is the only solution that's going to work for this is a solution whose derivative is itself. You get that? Right? Because that's the only way that I would be able to ever come to 0 is if the same base term went in for here, and then I can solve for particular values of P and Q. And so there's really only one function we know whose derivative is itself, and that's the e to the x function, or actually the e to the t function, excuse me. So let's do that. Let's say that x is equal to e to the t. But I don't want to just test e to the t. I want to test e to the something t, right? So let's just call it e to the lambda t, right? And so since we're just doing generics, let me also throw a constant in front of this, right? So e is equal to, or the x is equal to c e to the lambda t. So let's look at this and see what we get. All right, I'm going to plug that into here, and I get the following. I'm just going to go to a new sheet of paper. Well, let's just do the prep work here. dx dt is equal then to c lambda e to the lambda t. And then the second derivative of that has got to be equal to c lambda squared e to the lambda t. Okay? So now if I put that all in, I got 0 is equal to c lambda squared e to the lambda t, that's my dx, d squared x dt squared, plus p, and then dx dt, c lambda e to the lambda t, plus q, and then times x, which is c e to the lambda t. Now this is really good because if you notice, a whole bunch of stuff is going to cancel out. I notice I've got a c in every term that I can divide through, and I've got an e to the lambda t that could divide through. Oh, okay, that means that there are true solutions to this equation as long as lambda squared plus p lambda plus q is equal to 0. Well, that's pretty simple then. So what is lambda? Well, that's interesting because then lambda must have multiple solutions, meaning this second order homogeneous differential equation always has multiple solutions. So here we go. So lambda is equal to, well, negative b plus or minus the square root of, well, in this case, p squared minus 4 times a, which is 1, c, which is q, all over 2a, so over 2, okay? So that's what lambda's got to be equal to. Oh, well, that's really super interesting for a number of reasons. Notice then a couple of things. The discriminant then becomes the most important thing for us, right? Because if p squared is greater than 4q, I'm going to have 2 real roots. If p squared is equal to 4q, I'm going to have 1 real root. And if p squared is less than 4q, I'm going to have 2 imaginary roots. Okay? Hopefully that gels with your understanding of what's going on. So what I want to talk about, well, what's true with the simple harmonic oscillator? Well, let's go back to what our general form of the equation is. So with the simple harmonic oscillator then, SHO, well, let's see. What's in the p place? Oh, there is no dx dt term, so p is equal to 0. Interesting. But q is equal to what? Well, looking at it, Q is equal to K over M. So let's see what we get. We get lambda is equal to 0 plus or minus the square root of negative 4K over M over 2. Well, that's gross, because if you think about that, I've got plus or minus. The 4 is going to pop out of that and go away. I've got negative the plus or minus the square root of negative K over M. Let's make that neater by pulling out an I. So I've got I K over M. That must mean that if going back to the solution we said before, where x had to equal c e to the lambda t, that x was actually equal to c e to the positive I k over m t, and c e to the negative I k over k over mt. We're like, what the hell is going on with that? And that's where we employ a little bit of trickery, because we know something. We know from our previous studies, well, that if you have e to the, say for example, it, that I could write that in a different way, right? That could be written in terms of cosine of t plus I sine of t, right? We actually proved that, if you remember, because we looked at the Maclaurin series expansion of cosine of t and of sine of t and of the Maclaurin series expansion of e to the it in order to get that. And so if we look at these solutions, then we have c, and just for sake of argument, let's call c, I don't know, a cosine of, and rather than just having t here, I have k over mt, cosine of k over mt plus I sine k over mt. Or actually, this should have an a in it as well. Oh, remember going back to this, where we said that it was an imaginary axis and an x-axis? Well, there's your imaginary part of that simple harmonic motion right there. It comes from the solution of the second order differential equation that allows you to solve this problem, which is why we just take the real portion of it and we don't care about the imaginary portion of it. So there you go. The plus phi just comes from the starting position. I could have tacked that on here as well, and it wouldn't change any of the derivative work if I had gone back and guessed that the solution was this plus a constant. That would have changed none of the original work. So there you go. So that imaginary stuff pops right out. Now, that's kind of cool that we can use that to solve even more complicated things. Going back to the original piece, though, p is equal to 0. Well, when wouldn't p equal 0 for this? Oh, I mean, like, why would I ever have a p term? Oh, I would get a p term if there was something in this function that had a velocity term. What could possibly have a velocity term there? Well, going back to the sum of force equations, I could have a velocity term because this term came from the spring force. Well, what other force could exist? Oh, there could be an air resistance force, and the air resistance force is negative BV. There's your dx dt term, where P then would be, or the sum of force equation would end up being negative kx minus BV is equal to max. And then I would get a second order differential equation, which would be 0 d squared x dt squared, and then plus b d x dt, and then plus k, actually I have to divide the m, b over m, and then k over m x. And then this would be non-zero, which would make the solution from the simple harmonic oscillator just a little bit more complicated, because my p would not be 0, but b over m, which seems to complicate matters. So let's just take a quick minute to see what that would do, right? So I know that lambda has to equal negative p plus or minus the square root of p squared minus 4q all over 2. And so now if q is equal to k over m and b is equal to, if p is equal to b over m, lambda is equal to now negative b over m plus or minus the square root of b squared over m squared minus 4 over k over m all over 2. Now, that's a really awkward solution. Let me just make this a little bit easier. If I just take this and make it b over 2m plus or minus the square root of, and I pull that 1/2 in, and I do b squared over 4m squared, and make this equal to k over m then. If I do the following, if I make something, let's just call it gamma is equal to b over 2m, then I could just make this nice and simply negative gamma plus or minus the square root of gamma squared. Now we already know k over m is equal to omega squared for the simple harmonic oscillator. I've got this nice simple term there. Well, it's not really simple, it looks a lot better. But now what we can do here is the following. So let me just write this here, that omega is equal to the square root of k over m, gamma is equal to b over m. So now, here's the thing. Notice, using this idea here, it was only when I had an imaginary number here that I ended up with sines and cosines. Meaning, for this thing to go into any sort of periodic motion, omega, whether it's alpha squared, has to be less than omega squared. Meaning, the thing that's talking about how strong the resistive force is has to be weaker than the restoring force, right? So if the restoring force is stronger on average than the resistive force, then therefore I'm going to get an imaginary number. Okay? And that's really helpful to get that imaginary number, because then, therefore, this thing goes into a harmonic motion because it's going to have sines and cosines. So let's do the following. Let's pretend that omega squared is much larger than gamma squared, meaning that the resistive effect is like a little bit of air resistance, no big deal. That means, therefore, I can say that lambda is equal to negative gamma plus or minus, then underneath here, if this is much larger than that, then this is not really that relevant. So I can just collapse the entire term to negative omega squared, and negative omega squared, square root of that, is negative I omega, right? So what does that mean then? Well, going back then, our solution is x is equal to c e to the lambda t, we said. So that must mean it's c e to the negative gamma plus or minus I omega. Ugh, that's gross. So let's actually just write that c e to the negative gamma plus I omega, and then plus c e to the negative gamma minus I omega. We're not going to get too bent out of shape about which of these two things it is. But let's look at this, because this is gross. I'm just going to change that, folks, using my exponent rules, to negative gamma e, I missed the t here, excuse me, right? So all of this times t, all of this times t, all of this times t. So that's equal to negative gamma t e to the I omega t. right? Now, we've already shown that this ends up being sines and cosines. So this is e to the negative gamma t times what is functionally cosine of omega t, right? So notice then what we have is an oscillation back and forth at a certain period, but there's this factor, which is an exponential decay. So what that motion looks like is the following. If this is x and this is t, if I start at something here, what's happening here is the amplitude, because that's what we agreed that c was, is decaying over time. And so what I end up with is this. Now notice this term doesn't change the periodicity of what's going on, but merely changes the amplitude. And so where this just falls in the inside of the e to the minus t curve, right? So that curve is the e to the minus t part, e to the minus t. So what's happening here is something called a damped harmonic oscillator. And that's common, right? So that if you have like a spring going back and forth, and eventually over time it decays down to nothing, that's what's going on here. If it's air resistance, where the air resistance force is not that large compared to the spring force. And so that's a common solution there. Now, but that's only if that's true. If, as a secondary example, omega squared is just greater than this, it just becomes more messy, but you're still going to have an I pop out of there, which means that you're going to have still an oscillation. It's just, it's not the function is just not going to look as neat. But something interesting happens there in this analysis if, going back to that, let's actually go a couple pages beyond. I've got lambda is equal to negative gamma plus or minus the square root of gamma squared minus omega squared. What happens if gamma squared is equal to omega squared? Well, that entire term goes away, so lambda is equal to negative gamma. In that case, x is equal to c e to the minus gamma t. Oh, that object doesn't even ever get into harmonic motion. It just is an exponential decay down to t, right? So that's pretty, makes sense. If the resistive term is on the same order of magnitude as the term that's the restoring force, it probably never going to go, well, it's never going to go into oscillation. And then if gamma squared is larger than omega squared, notice that is now real. So this thing never goes into oscillation ever. This is something called a critically damped. It actually just goes into a much more dramatic decay, because there are two things adding to the decay rather than one thing adding to the decay. So this solution of the second order homogeneous differential equations, where the restoring force term is larger than the resistive term, is what yields all of our back and forth motion or periodic motion, and then we get these other factors involved in it. And so I just hope you enjoyed a little bit of deep dive into the math of this. I'm going to post a much longer reading on this if you're interested in it. I super am interested in all this stuff. So if this is something that you find interesting, you would encounter this in a second level mechanics course in college. This is not something that would be taught in an introductory mechanics course in college. You pretty much not encounter this until your second semester, sophomore year, maybe first semester, junior year, depending on the university you went to, because they would want you to have Calc 1, Calc 2, Calc 3, as well as some differential equations work under your belt.